Alright, let's start off calculus with something that hopefully we are all familiar with. The topic is lines. So much of calculus is focusing on this concept of local linearity, meaning that even if a function curves, if we were to pick a random point and stay very, very close to that said point, then the function is going to behave very much like a line. So if we were to example graph the function of y equals sine of x and y equals x on our calculator, there is obviously not the same function on that given screen at the same time. But if we zoom in, let's say at the point 0, 0, because I would have both of them on my particular graph at that time, no matter how much I zoomed in at that point, then they're both going to end up looking like lines no matter how curved one of them starts and how linear the other one might be. If you don't believe me, let's pop on over to Desmos to check this out. Alright, so I've popped on over to Desmos. I've got my y equals x as my red and my y equals sine of x as my blue. So what's happening here is we see, hey, this one's curved and my y equals sine of x, and my other one is very, very linear. But I said, okay, let me zoom in on the point 0, 0, which happens to be my origin. So I'm going to zoom in at the point 0, 0. Alright, I see fewer curves, but that sine of x still looks curved. So let me zoom in some more, still towards that point of 0, 0. And as I'm getting closer and closer to this point of 0, 0, I really can't tell which function started off as a line and which function started off as a curve. Because if we pick a certain point and we zoom in, any kind of function that we choose is going to end up looking like a line. Alright, let's pop back over to the notes. Alright, so going along with lines, we have this thing called slope, which hopefully we are slightly familiar with at this point in time. So slope is often given by the change in y over change in x. If you are unfamiliar with these symbols with the triangles, those are just the Greek letters delta, which usually stand for the change in and all that kind of good stuff. But more commonly, we've seen it as y sub 2 minus y sub 1 all over x sub 2 minus x sub 1. Those both mean the same thing. One just looks a little bit nicer and takes up a little bit less space. So, keeping in mind, a vertical line has undefined slope. Vertical meaning it goes straight up and down. And in this case, we'd have something over 0. We can't divide by 0. Our brain goes boom. It's a bad day in math class. Meanwhile, a horizontal line, one that goes straight across, should have a slope of 0. Parallel lines have slopes that are the exact same. And perpendicular lines have slopes that are negative inverses. Alright, so going forth into calculus, we should be starting to think of slope as the rate of change. And the slope between 2 points is more commonly going to be referred to as the average rate of change. Alright. Me scrolling down, I'm next going to deal with those equations of the lines. There are 3 main types of equations of lines. The most common, the one that you guys probably got burnt out on in Algebra 1, is that slope-intercept form, which hopefully we remember is that y equals mx plus b, where slope is going to be our m, and that y-intercept is going to be my b. In calculus, there's a much easier way to write an equation of a line, and that is point-slope form. We've talked about this in Algebra 2 and in pre-calculus, but that one's a little bit not as stuck in our heads. That one was just that y minus y sub 1 is equal to m times the quantity of x minus x sub 1. Where that point is just going to be that x sub 1 comma y sub 1, and my slope, just like slope-intercept form, is still going to be m. Alright, and in order to write an equation, really all that comes down to it that we need is a point and a slope. Hence the name point-slope form. Alright, and then another format that we can use is called standard form, or it's sometimes called general form. It's just not as common to hear it called that. And it's as easy as ABC to remember. So I've got AX plus BY is equal to C. This form is pretty useful when trying to find your X and Y intercepts. And the slope is honestly pretty easy to find from this general form as well. A couple notes about this particular form, just because we're not as probably familiar with it. A, B, and C should not be fractions. A is almost always positive. B does not have to be positive. And that's about it. A is always with X, B is always with Y, C is always just some general number. That's about it. So, example 2, which of the following equations has Y written as a function of X? That's just a fancy way to say, hey, which one of these is Y equals? Well, that would be that slope-intercept form, that Y equals mx plus b, that slope-intercept form. Alright, and then my point-slope form written as that Y, written as a function of X, all I've got to do is put that Y minus Y sub 1 equals m times X minus X sub 1 into a Y equals form, so all I've got to do is add this bad boy over, and I should be done. So that should just be Y is equal to m times the quantity of X minus X sub 1, now plus Y sub 1. And we're done. Cool. Moving on. Alright, example 4. Sorry. We need to find an equation of a line passing through the point of negative 2, 4, and having the following characteristics. So it says, hey, we've got a slope of 7/16. Well, we've got a slope and we've got a point. Fancy that? We have an equation for that called point-slope form. So that would be that Y minus Y sub 1, which in this case is 4, is equal to m, which is my slope, which is 7/16, times X minus X sub 1, so minus negative 2 is just going to turn into plus 2, and we're done. We just need an equation. We don't have to put this in slope-intercept form all the time. You guys don't have to distribute, because that's gross. Alright, moving on then. Parallel to the line of 5x minus 3y is equal to 3. Alright, first thing that we probably want to do is try to find the slope. Alright, so a lot of you guys are like, okay, I can put that in slope-intercept form, which you can. It's a valid way to try to find that. However, the cheap way to try to find slope in standard form is actually using this little bitty formula that is negative a over b. So plugging in my a, I would get negative from the formula, that 5 from that particular equation, and then my b is negative 3 in that case. So all in all, my slope is 5/3. Cool. So now I've got a point that they gave us and a slope. So again, I can use that point-slope form, which is going to be that y minus 4 is equal to now 5/3 x plus 2. Bada bing, bada boom, we're done. Next one says perpendicular to that same line of 5x minus 3y is equal to 3. So perpendicular just looks at our slope, and we flip it to make it the reciprocal, and we make it the negative. So if it was negative to begin with, it's going to become positive. If it was positive to begin with, it's going to be negative. So my slope should be now negative 3/5. And I've got a slope, I've got a point. We can use point-slope form. So I've got y minus 4 is equal to negative 3/5 x minus negative 2, which again is still plus 2. Alright, the next one says, hey, I need to pass through the origin. It didn't give me my particular slope, so we got to find it. We've got 2 points. So that goes back to at the beginning, that change in y over change in x, that y sub 2 minus y sub 1 all over x sub 2 minus x sub 1, change in y over change in x. So this time I've got my 2 points, which are negative 2, 4, and I've got 0, 0 as my other point, because the origin always refers to that 0, 0. So I've got y sub 1 is going to be 4. The x sub 1 is going to be negative 2. So I've got 0 minus 4 over 0 minus negative 2. So simplifying this down, I should get negative 2. I should go ahead and now I've got a slope, I've got a point. I don't care which point you pick. I am honestly going to pick 0, 0 just because it makes my life easier. So in this case, I would have y minus y sub 2, which is 0, is equal to my slope, which I just found was negative 2, times x minus x sub 2 in this case, which is 0. Bada bing, bada boom. Clean this up a lot, so I'd get y on that side, because anything minus 0 is still itself. And then just distribute that negative 2, which is just going to give me negative 2x. Great. Alright. And then the last little example that we are going to look at is parallel to the y-axis, which is that x equals line all of the time. Again, that's just because it's going to have the same x value over and over and over. If it is a line that is going straight up and down, your y values are going to change. Your x value is not if it's going straight up and down, just like your y-axis is. So technically your y-axis is that line of x equals 0. So I need an x equals line. Well, if it's got to be parallel to the y-axis, but also passes through this point, that means that my x value has to match my x value of my point, which is negative 2. Alright. Should be everything. I'm not going to make you guys do this because, well, this requires a calculator and just a lot of time, and honestly, we don't really need it. So I hope you guys have a great rest of your day, and I will see you guys tomorrow.